everyone. Today we are in chapter 6, we will go over only 6.1 and 6.2, both sections about spring problems. Okay, so chapter 6 about application of linear second order equations, and 6.1 spring problems number 1, and 6.2 spring problems number 2. Okay. All right, so let's do this. All right, so spring mass system is an equilibrium when the object is at rest and forces acting on it sum to zero. Okay, I have a nice picture. Let me change the it. Okay, so we have equilibrium position, right? So this is the one when y equal to 0. And we say that yb displacement of object from its equilibrium position. Okay, so y equal to 0 is the equilibrium position. And look, displacement means change the place, right? Change the position, right? So look, from equilibrium, and we have upward. The spring is upward, then y is greater than 0. And spring is downward, right? Then we called y is less than 0. Make sense? Okay. Now, we have the force. And let's make a F, yeah? F equal to negative mg. So we did this one last time. M is mass, and then G is gravity, right? So the gravity is pulling down, so we're using negative mg, right? Okay, now they have different force. Force in the case S. S means spring, resisting, change in its length. Yeah. Okay, so we're using first letter from the spring, and then we denote like F sub S. All right. Okay, now what is F sub S? So this formula comes from Hooke's law from the physics. Yeah. Okay, so K times, what is K? Just a spring constant. And we called this one as delta L, right? Delta L means the change in L, right? So what's the change in L? So we are using the first letter length. So uppercase the length L. Make sense? So delta L is natural length. What is the natural length? That means there's no mass attached. So it's naturally make a stretched, or compressed, but they should be have a mass, right? But yeah, you know what I'm talking about, right? Natural length about the delta L. Let me write down. Delta L. Okay, now I have a note here. Note, if the spring is stretched, then like stretched earlier, delta L natural length will be bigger than 0, right? Stretched, right? And then the force of a spring is greater than 0 as well, right? Then the spring force is upward. Yeah. Okay. Now we have a spring is the compressed, and the natural length is less than 0. and the spring force is less than 0, then spring force is downward. So we can just notice that, right? It's less than 0. Spring force is downward. And then spring force is greater than 0. It's upward. Yeah, like what we had y is greater than 0 earlier, upward from equilibrium, right? And we had y is less than 0 for downward, right? Okay, now, so we had the force in terms of gravity, yeah. And then we had the force spring force, yeah. Now we have damping force, not the dumpling, damping force, looks like. All right, so damping force, we are using first letter D. Yeah. So what does a damping means? Yeah, damping force. So that means, let me see, resist the motion. So we have, look, so we have a damping force. First of all, the formula has negative C and Y prime. Okay, then we have that damping force. If C is greater than 0. All right, then we have that resist about the motion. What this means? This means due to air resistance or friction. All right. Okay. In other words, undamped, if that C constant equal to 0, then everything is 0, right? If C equal to 0, everything will be 0. Yeah. Okay. Once again, we had force in terms of gravity, which is negative mg, and Hooke's law about the spring, right? So spring force, K times delta L, and we have a damping force. So we denote F sub D, which is negative C times Y prime. And now we have external force, F. We just denote F, yeah? Nothing else in the subscription. Okay, so other than the force due to gravity, okay, now the motion is free. So motion is free means free of external force, gravity, or fraction, not the fraction, friction, and so on, right? So if that case, we say that the force equal to 0. If motion is forced, then it's not equal to 0. So motion is free, then we're using the force equal to 0. If not free, forced, then we say that equal is not equal to 0, yeah? Okay, not force. Now, we have Newton's second law. Yeah, so we did this one before, right? So the force equal to mass times acceleration, right? Okay, so we know that if we are using y, right? Let me write down, note, y, the equation, right? So y prime, velocity. Okay, how about displacement, right? So displacement and so note Y is displacement. Then Y prime is velocity, right? And Y second prime is acceleration. So F equal to ma, that means m times Y second prime, right? Make sense? Why we get the Y second prime, right? Okay, now look, we have a gravity force, and then we are using all forces from above. Yeah. So we learn the force, uh, damping force. Yeah. Plus and spring force. And then other than above, we had just regular force. Yeah, right. Right? Okay, now we do replace. So we say that the damping force minus c times y prime. Yeah. Now, how about Hooke's law, right? That's the spring force. So spring force, we have K times delta L, right? So we replace here. So Hooke's law, K times delta L, yeah? Okay, then delta L means that the natural length, right? So we have natural length from like also displacement, right? So about the change in position, right? So we can notice that, or we can note that delta, the lowercase l minus initial length, so final length and initial length, yeah? So there will be, we indicate that k times delta L minus Y. So basically, we express delta L as delta lowercase l minus Y, and we keep the K. Make sense? Okay. Now, we do distribute. Then we have K delta L minus KY, right? Okay, nothing changed. All right, then we say that mg equal to k delta L, which is same as k delta lowercase l, okay? So we make equal to 0 because the gravitational force, the spring force must be balance each other out. So we make mg, which is the gravitational force equal to spring force. Make sense to you? Say just uh-huh. Okay, now, so everything together, right? So they are equal to same, so which means 0, right? And then I just rewrite negative cy prime minus ky plus f. Yeah, all right. Right side. And then what we start with? MA, right? So MA equal to M times mass times Y double prime, right? Okay, now we start for F. Another force, yeah? That will be, everything is other side. So we have M times mass times Y second prime, which is acceleration, plus c times y prime, which is velocity, and plus k times y equal to the force, right? Can you see that? Y double prime, Y prime, Y. Yeah. Okay. That is, we derive the equation of a force all together, right? Okay. Now, whoo, you guys understand. All right, we have another one. Simple harmonic motion. Now we do one problem. We are done for this section. We keep continue spring problems. Okay, in next section. So we have a simple harmonic motion here. Undamping. So we had a damping, damping, undamping, right? Undamping force. So F sub D equal to negative C Y prime. So damped. Then if C is greater than 0, undamped, C equal to 0, right? Okay, so undamping, that means C equal to 0. Yeah? Okay, so um, undamping means no resistance. Yeah? Then damping means resistance. Yeah? Like air resistance or friction, like that, right? Okay. Now, from this equation we have, right? So m y second prime plus c y prime plus k y equal to f. All right, then c equal to 0 because on damping. Yeah, c equal to 0. Okay, now we give it to the force equal to 0. That means free, right? If free, I mean the force is 0, then motion is free. We had that this one earlier, right? And then the motion is force, then F is not equal to 0, right? Yeah. Make sense? Okay, now uh then we have an equation since we have motion is free. So we make other side equal to 0, then we have equation m times y second prime plus ky equal to 0. All right? So we derive another equation. So we call this as a simple harmonic motion on damping. Okay? All right. So let's do one question. Then we are done for this section. Okay. So let us do this. An object stretches a spring 6 inches in equilibrium. Set up the equation of motion and find the general solution. And find the displacement of object for t is greater than 0. Initially displaced 18 inches above equilibrium and given on a downward velocity of 3 feet per second. Yeah. Okay. So let's see. First of all, we have inches, but they talk about the feet. So we want to convert to the feet. Yeah. Okay. So 6 inches times 1 feet over 12 inches, right? Okay. Then 6 goes to the 12, 1/2 feet. Yeah. Okay. Let's start with that. All right. So the first part, Okay, the equation we had earlier, this one, I want to use that, right? Yeah. So in order to use this one, we derive everything from beginning to here, right? Okay, now, um, look, I want to make y prime itself, okay? So that means we divide by m every term, right? Okay, then we have y second prime plus k over m, y equal to 0. Yeah. Okay, now what is a k over m? So look, mg equal to, we had earlier, right? So we had, look, previously they are equal each other, right? In that case, remember? Oh, you guys cannot see? Yeah. Sorry, this is a little bit slower. So mg equal to k times the delta L. Yeah. Yeah. This is slow. Sorry about that. And they are equal each other, right? Okay. So I am using this one. Let me copy. Copy. So we have, yeah. Okay, now solve for k over m because we had k over m here, right? Okay. K is here, m is here, right? So we divide by m, both sides. So we have z equal to k over m delta L. Yeah. Okay. So we want to solve for k over m. So we have more than k over m in right side. So we want to divide by delta L. Delta L. Okay, so then we have GL. G over delta L equal to K over M. Yeah. Okay, so we can express K over M, which is G over delta L. Yeah. Okay, now we had, what's the G? Not G. G is, we can express as a feet per second square, then 32 feet per second square, right? Because we want to have same unit with this velocity, right? That's why we convert to from inches to the feet. Make sense? Okay, now what's the G? G in the case 32 feet second square, right? Over delta L. Delta L will be, what was it? One half feet stretched, right? Okay, so there will be one half feet. Okay, so it will be K over M. Now we simplify. What do you get? So 32 times one half, 2, right? Yeah. And K over M, which is 64, right? Make sense? Okay, So we will use k over m will be 64 there. Okay, then y prime plus y equal to 0. Yeah? Okay, what can we see? We can switch it to r squared plus 64 equal to 0, right? Yeah. Okay, let us do that. So that will be r squared plus 64 equal to 0. What's the r? Plus minus square root minus 64. And that will be plus minus 8i. Yeah. Okay, now I brought this one here. It's been a while, right? For me, for you? Yeah. Okay, so we have a complex conjugate root, right? So the first root will be lambda plus I omega, and second one is lambda minus omega W. Omega W? No, sorry, I omega. Okay, general solution will be that. Boom, we done, right? Okay, so there will be omega. Yeah. What about the lambda in the case? Yeah, lambda will be the 0 because there's no real part, right? So we can express this one. Note r equal to 0 plus minus 8i. There will be lambda. There will be lambda, right? Okay, so e to the lambda, y equal to e to the lambda, x. We have a sine 1 cosine omega. This is omega, right? So 8x and plus sine 2 sine omega, right? All right. So lambda in the case is 0. We will get just this one, right? No space. How about this one? Oh, we have a second part, yeah? Okay. Then y equal to e to the 0, sine 1 cosine 8x plus sine 2 sine 8x, yeah? So that will be, the solution will be sine 1 cosine 8x plus sine 2 sine 8x, yeah? That is the solution. Make sense? Okay. All right, so second part. Yeah, that is a general solution, right? Okay, second part we have, okay. So 18 inches. Also, we need to convert to the feet. So 1 feet corresponding 12 inches. Then we calculate. Then there will be 1.5 feet. Yeah. Okay, initially displaced 1.5 feet, so y of 0, right? Initially means 0. Okay. Then given downwards, so we are using the velocity 3 feet per second. So since downward we are using negative, and we know velocity, we're using y prime, right? So y prime of 0 equal to negative 3. Yeah. Okay, now from the general solution, basically we want to find the C sub 1, C sub 2. All right? Hold on 1 second. Look, they using T, right? So I want to use a T here too. T? Yeah. So T, T, T. Let me fix everything, all right? Later. So, oh no, not this one. Okay, let me write down. Y equal to, in terms of T, so Y over T equal to C sub 1 cosine 80 plus C sub 2 sine 80. Yeah. Okay, we use Y of 0 equal to 1.5 and then Y prime of 0 equal to negative 3. Yeah. Okay, now what's the Y prime of T? Derivative of cosine 80, which is negative sine 80 times 8, right? So 8 C sub 1 negative sine 80. Yeah. What's the derivative of sine 80? So 8 times C sub 2 cosine 80, right? So plus 8 C sub 2 cosine 80. Okay, now y of 0 equal to 1.5. So C sub 1 cosine 8 0 plus C sub 2 sine 8 0. Yeah. Okay, so there will be 1.5 equal to cosine 0 equal to 1, right? So C sub 1 sine 0 equal to 0, right? So C sub 1 equal to 1.5. Yeah. Okay. Now, y second prime of 0 equal to negative 3, right? Then negative a c sub 1 sine a times 0 plus a c sub 2 cosine a 0. Okay, this is 0 and we have negative 3 equal to 8 c sub 2 then. Yeah. Okay, what's the c sub 2? C sub 2 equal to negative 3 over 8. Okay, now 1.5 we can express as a fraction as 3 over 2, right? Okay, then we will get y equal to C sub 1, which is 3 over 2 cosine 80 plus C sub 2 negative 3 over 8, right? Sine 80. So y in the case is displacement. And it's in feet. Make sense? Okay, so we finish this section and I'm gonna see you in spring problem second part. All right? Thank you for watching. Bye.